This is Om Kedareshwar Kiran from 5th Sem Electrical Department. Today I am presenting about data-driven control in nonlinear systems with input and output data. So let us know about the data-driven control, what it is going to show. It generally shows that the transformative fields and the data-driven control focusing how efficiently the complexity and of nonlinear systems can be managed through input and output data, and also casually the recent breakovers through methodologies and key points of the foundations preformed before implications. For engineering and scientific applications, there are different data driven control, not only non-linear. We can also bring it to the linear static, and it can be run further efficiently for the transformative field of data driven control. And next one, the challenges of nonlinear system control. What are the different types of nonlinear system controls and what are the challenges we face in the nonlinear systems? Complex dynamics. Nonlinear systems relevant the various domains like aerospace, robotics, and biology exhibit the often unpredictable behaviors, making the inherent to difficult to control. In generally, the control systems, the nonlinear data for a feedback system, it is not connected, then it exhibits the unpredictable behavior of the data. So nonlinear systems in this complex dynamics, they are going to tell it about is they use in aerospace, engineering, robotics. So next one is model dependency. Traditional control approaches heavy relay and mathematical models, which are frequently unavailable and prohibited a complex driven nonlinear system. So the model dependency is about the control of approaches, how the nonlinear system is approached to the different prohibited complex driven nonlinear systems. Data as input is in practical scenarios only input output data measurement of what undergoes the system calibration and obtain how the significant hurdle and control design. The control design doesn't change according to the complex dynamics. The data input and output must be changed because to control direct control design. So next one is direct control design. The fundamental question arises, how directly synthesized effective controls in the system, usually input and output available data by passing the complex models. It is a general question, how the input and output data is complexity and effective controls order the measures taken with direct synthesis. I'm sorry, but I'm not aware of this. So next one, from modeling based to data driven control. Traditional control limitations and data driven shifts. Classic control methods such as feedback, linearization, uh, reboost control, and model predictive control (MPC). The powerful often require a system for model full scale statements. Full scale statements means the exhibit the split full state measurements. Nothing but full scale statements. It has a complete statement. These these all applications we use in real world applications. These all predictive control. It is a predictive control where we use the real world applications to complex the unmeasurable measurements. The data driven shift is control mark and shift, enabling the direct linear control loss and measured data. This approaches facilities model to free model light control, opening new avenues, managing high complex uncertainty. Nonlinear systems, effectively they may or may not categorized with the first principles of model of traditional control limitations. Next one is breakthrough linear controls via approximate non-linearity cancellation. Sorry, non-linearity cancellation. Approximate means through approximate non-linear cancellation, how the linear breakthrough controllers devices works. Here in that there are categorized into three main types: semi-definite programming, stability, and real world applicability. Semi-definite programming, it generally introduced about the method of programming where input and output data synthesis dynamic output feedback controllers. Dynamic output feedback controllers means the exact, not exactly, but it can vary the feedback controller in different types of semi-definite programming. Stability is about the approach provided region granted closed loop stability, ensuring that the system exhibits desirable linear like behavior despite it undergoes with non-linearity. Real world applicability, it is a crucial work to address the particular demonstrating efficiency and noisy without direct system states, making robust real world development. So these are about the linear controllers through approximate nonlinear cancellation. So direct driven state feedback control general nonlinear system. Before going into this, let us know about the control systems introduction. In generally the control system, the feedback, it works on the feedback when the output acts as a feedback to the input, and then automatically the system enhances the output feedback given through the input and work more efficiently. So in this case, the velocity from LPV means linear parameter varying. Linear parameter varying means representation of direct system data capturing non-linear dynamics efficiently. Non-linear dynamic efficiently means the non-casual and casual system, the dynamic efficient, how it works. And stability, there is a method of synthesize non-linear state feedback controller ensuring the stability, meaning the system consists returns desired equilibrium point. Single data sequence, as we know the basic function it is. Challenges and examples, these approach have been convincingly demonstrated through complex linear systems, including challenges and scenarios like unpredictable disks and different unbalanced disks, unpredictable disks, and highlighting its board applicability. Next one, driven non-linear control. It is driven non-linear control means the feedback linearizable systems. In generally, it rescues about the feasibility and stability. The approach, these rescue and feasibility approach guarantees the ensuring the solution exists each control iterations mean the following uh, distributions particular stability distribution, providing robust performance. Predictive control with basic functions, the frame uses basic function and noisy input output data to implement predictive control, allowing the future system behavior predictions and control adjustments. Complex system applications, this methodology has been successfully applied highly complex system and reboost efficiency in accurate scenarios. So data driven feedback linearization via model predictive control. Non-linear system ID, linear behavior, robustness, validation. These four categories come under the amplification of the predictive control, how it amplifies. In linear behavior, we see the input and output characteristics in a wide range of operating conditions and also design inherently non-linear systems. Validation is the validation system defaulting oscillations and high predictions with the different type of particular usability and scalability. So next one, Pop Popman operate basic Newton Raphson control from data. So he's a scientist who created a theory. So data driven prediction, these enables accurate prediction and uh, estimation purely from data, eliminating the unpredictable dynamic models, and also exploit the dynamic models and simply analysis. Variable grain integral control is about the feedback frame which controls the basic real-time data and enhance applicability. Validation of high nonlinear systems and methodology scientifically. mm, It generally enhances the particular applicability, offering the robust solution and wide range of control challenges. The wide range of control challenges generally having the adapting control effort. So practical impact on future direction reduces model dependency and adaptivity, scalability, control, and linear challenges, emerging trends. These are normal data-driven control fundamentals, and also it reduces the complexity. These all methods furtherly helpful to dissipate the program challenges and reboot server noise efficiency. So, at the last conclusion, towards a new era of data-driven nonlinear control, we withstand the control engineering and applicability of input and output data unlocks and capability of controlling high complex nonlinear system. Recent breakthroughs provide only theoretical, fundamental, and practical algorithms. So, future control is about the integration and advanced theory, computation, computational power, and real world strategies enhancing the data driven control and methodologies. Thank you.